Recursion is not a difficult concept, and actually the code is tremendously simple, but people tend to struggle with it because it seems to be one of those things where it's not very intuitive. When you see it on the screen, everything that I'm going to tell you in this lecture is going to make perfect sense, and you're going to go, I don't know why this is so hard. Why are people freaking out about this? But when you actually go to write it, you're going to realize that it's sometimes just very difficult for you to figure out how to do it. So I'm going to show you that there's two easy steps that you will always follow, and if you do those two steps, then life will be good. So we're going to start off with a weird example. So I'm going to come over here and I'm going to show you some playing cards. So hopefully you guys have ever seen playing cards before. And I picked out of the deck some 6 random cards. Well, they're not random, obviously. They're very specifically 6 cards. And what I want to do is I want to arrange them in some order. So right now they're arranged numerically. So I have 1, 2, 3, 4, 5, 6 basically. They could be arranged the other way around. So like I could have 6, 1, 2, 3, 4, 5, or I could have 6, 2, 3, 4, 5, 1, blah, blah, blah. All right. So you might wonder, how many different ways could I arrange these 6 different cards? And this is a mathematical function called factorial. But I'm going to explain it to you because it's actually a pretty simple concept. So down here in the bottom, we have 6 places that I'm going to put these cards. So my question is, if I'm going to put the first card into this box, how many choices of cards do I have right now? Well, the answer is I have 6 choices. 1, 2, 3, 4, 5, 6. So when I'm placing something in this spot, I have to choose from 6 different options. So I'm going to choose the 4 of hearts for some reason, and I'm going to put it in there. So there were 6 choices here. Now how many choices do I have when I'm placing this card? Well, I've used up one of my 6, so I no longer can put that one in here because it's already used. So how many are left? Well, there are 5. So I'm going to arbitrarily choose this ace, and I'm going to put it into this one. So for this spot, I had 6 choices. For this spot, I only had 5 choices. So let's look at this next spot. How many choices do I have here? Well, I have 4. So I'm going to arbitrarily pick the 6, and I'm going to stick it in there. For this one, how many choices do I have? I have 3. For this one, how many choices do I have? I have 2. And finally, for this one, how many choices do I have? I only have 1. So how many choices did I have here? I had 6, then 5, then 4, then 3, then 2, then 1. And this is the number of options that I had in total. It will be 6 times 5 times 4 times 3 times 2 times 1. Because for each one of these possibilities, if I come back up here to where we were just dealing with there being 2 options, so this is 6 times 5 times 4 times 3. You might be wondering, well, why is it times 2? Well, because there are 2 different ways that I can arrange these last 2 cards. I could do it like this, or I could do it like this. That's why it's times 2 different options. So regardless of what I've done before that, I had 2 choices when I got to here, and by the time I get to the last card, there's only one way I can arrange it. So 6 times 5 times 4 times 3 times 2 times 1 is a large number. I think it comes out to 72, but let's do it in a calculator. 6 times 5 times 4 times 3 times what did I do? Times 2, and I don't have to do times 1 because we know that times 1 is just going to be the same, but just for giggles, I'll do times 1, and you see the number is 720. So it turns out there are 720 ways I could rearrange these cards. Cool. This is the concept of factorial. All right, so jumping away from those and coming back over to the slide deck here, let's talk about how we might go about coding this. So it is certainly possible that you could code this using iteration. You could have a loop that chugs through and keeps multiplying the number by a number minus 1 each time. Here you can see 6 factorial, as I just described, is 6 times 5 times 4 times 3 times 2 times 1. If I had asked you to calculate 75 factorial, well, that's a lot. The answer is still the same. It's 75 times 74 times 73 times 72 times 71 times 70 times 69, all the way down until you get to 1. But there's another way to describe this, because if we go back to this picture here, and I say 6 factorial was equal to all of this, well, if you ignore that first one, what is that? Well, that's 5 factorial, right? Because that's 5 times 4 times 3 times 2 times 1. So if I just break it up into 2 chunks, another way to phrase it is that 6 factorial is actually equal to 6 times 5 factorial. And that's a much shorter way of writing it. So that's what we're going to do with 75. 75 is actually equal, 75 factorial is actually equal to 75 times 74 factorial. And if we break that out a little bit more, well, what's 74 factorial equal to? 74 factorial is equal to 74 times 73 factorial, and so on and so forth. 73 factorial is equal to 73 times 72 factorial. Okay, so there's an important thing to notice about this pattern. In each case, the operator that we're trying to calculate here is this factorial, which is represented by that exclamation mark. The definition of factorial includes a definition of factorial. What do I mean by that? I mean, in order to calculate 75 factorial, I need to be able to calculate 74 factorial. So this is an example of recursion. I'm taking the answer to my question is going to also involve the same method that I'm currently implementing. Or to phrase that in a more reasonable way, I am going to call myself in order to get my answer. And that's what's happening in recursion. This is why you need your brain in backwards. So let's go through this for just a second. So 75 factorial is 75 times 74. Cool. 74 factorial is 74 times 73 factorial, and so on and so on. Obviously, this is a very large stack. I would have to say 73 factorial is 73 times 72. 72 factorial is 72 times 71 factorial. 71 factorial is 71 times 70 factorial, and so on, all the way down until I get to what I mentioned before, which was the 6, which you'll eventually get there, and then all the way down to 2 or 1. So how is this helpful? I mean, this is just confusing. Why are we even talking about this? Because eventually at the very end of this list, we know what the answer is. I know that 1 factorial is just 1, because it is 1 times nothing, which is 1. So we know that the answer to 1 factorial is 1. And eventually, the last equation that would have been on this list is 2 factorial, which is equal to 2 times 1 factorial. And since we already know what 1 factorial is, we know that that would actually equal 2. And then once we've calculated 2, we could feed that into the previous one and calculate 3 factorial and calculate 4 factorial and work our way all the way back up to 75. All right. So a general way of writing factorial is that n, which can be any number that I want to calculate, n factorial is always going to be equal to n times n minus 1 factorial. Once you realize that, we realize it's fairly easy to write this in code. But there are a couple of things that we want to always think about when we're doing recursion. So the first thing is, how do you know that something is recursive? And the answer is, somewhere in the code of a given method that is recursive, there will be a call to that same method. So you will declare something along the lines of int factorial, and it will take in a parameter, and somewhere in the code of factorial, you will see a call to factorial. If you think about the last lecture where we had method 1 and method 2 that were being called out of main, you realize that we were calling a method that was not ourselves. That's why that was not recursive. We're just calling a method, which we've done a million times. You've been doing this since you started coding. You write a method that does one particular thing and then you call it. The thing that's new about recursion is that sometimes you're going to realize that the thing that you want to call right now is yourself, because you are actually going to make the answer. I know that's all very confusing. So, how do you know that you are dealing with a recursive method? The answer is you are always going to see a call to yourself inside of the method. That is going to have the effect of creating clones of the function, and each clone is going to have a slightly smaller problem to work. So the clones are eventually going to work their way back until you get asked, what is the factorial of 1? Once you get there, you have reached the terminating condition. and there must be a terminating condition, otherwise recursion would go forever, much like an infinite loop. Each one of the calls that you make should be sending you towards that terminating condition, because if they're not, you have a problem. So the requirements for a recursive function are you're going to have a recursive call inside of your function, meaning you're going to call yourself. There must be some way that this all ends, and each time you call yourself, you must be getting closer to that terminating condition. If you do those three things, you will succeed with recursion. If you don't do them, well, you're going to end up with some weird thing that just keeps going. So let's talk about knowing that you've reached the end. This is called the base case, and I need you to learn that word because it's going to come up in quizzes and tests. The base case is the simplest possible problem that you can get for this problem set. So for the case of factorial, the simplest problem that you could be asked is the factorial of 1, because that is defined as simply being 1. Everything else, you're just going to have to figure it out. But we know that the factorial of 1 is 1. So that's our base case. You will need to identify what the base case is every time you write a recursive function. And then you're going to have the problem broken up into 2 bits. The part that you can immediately solve, which in the case of our factorial is the factorial of 1, and everything else, which is what's going to be the recursive calls. All right, once you know your base case, it should be your simplest case, and then you're going to figure out how you can get closer to that one step at a time. All right, so let's look at each of these. So the base case, as I mentioned, is going to be either 1 factorial or 0 factorial. Weirdly enough, both of those are defined as part of the definition of factorial. Why? Because, well, math. 1 factorial is 1, and 0 factorial also turns out to be 1 because reasons. So don't want to worry about that. That's just a mathematical property. If somebody's asking you to write a recursive function, they're going to tell you what the rules are of that function. So somewhere in the definition of the question, it's going to say something along the lines of, please note that the factorial of 1 is 1. Okay, cool. So if we had our method factorial, we know that when n is equal to 1, we are supposed to just return the number 1. All right, so this is the beginning of our method. We are going to return an integer, hopefully. The method is going to be called factorial, and we have to know a number that we are trying to be calculating the factorial of. So if you wanted to do factorial of 3, you would pass in a 3 here, and then it would go through and do whatever it is that it's going to do. But eventually, if you were to call factorial and pass it in a 1, it knows immediately that the answer is 1, and it just returns 1. So this is our base case. So it's very important that you have a base case, and it's usually the very first thing in the method. It is, how do we stop? That's very important that you figure that out. All right, so if that's not the case, i.e. they gave you something that is not 1, then we're going to make our recursive call. So we know that the formula is that, let's say for 2 factorial, the answer needs to be, goodness, how did I do that? The answer needs to be 2 times 1 factorial. So to write that out in code, it's super simple. We're going to say return n, which was the number that was passed in, times the factorial of n minus 1. All right, why n minus 1? Because again, this is going to be 1 less than this. So the factorial of 2 is equal to 2 times the factorial of 1. Even though we are right now in the middle of defining how to calculate factorial, this is going to work. All right, so there are 2 very important things to notice about this code. The first thing is that you have a base condition which will end it. The second thing is that you are making your recursive call, and as you are making that call, something is moving you closer to the base condition. If you did not pass n minus 1 here, if you just passed n for some reason, A, you would calculate the wrong number, but B, it will go forever and ever and ever, because nothing about that is ever decreasing what's coming in here, and therefore it's never getting you any closer to this base condition. So super important. There will be a base condition that will at some point end this, and every time that you make a recursive call, you are getting closer to that base condition. If either of those things are not true, you have created infinite recursion, which is bad. So let's talk about how this actually works. All right, so we have our main method down here, and we are simply going to call factorial, which is our method that we just wrote up above, passing it the number 4 so that we can start off and see what's going to happen. So we're going to calculate 4 factorial, and eventually we're going to print it out. So as we saw in the last video, I need you to think about a function stack. And that's this magical little place over here where as we execute things, they're going to get pushed into the function stack for us. All right, so the first thing that happens is what? When you start a program, whether it's C# or whether it's Java, we are always going to begin with the main function. So the main function is going to get pushed into the stack. The main function has 2 things that it's supposed to do. It is supposed to call factorial of 4, and then it is supposed to print out the answer. Cool. So in our stack, we are going to write down the thing that we're going to do, which is f equals factorial of 4. Now, if you remember from the last video, what's going to happen is when you see a call to a method, we're going to remember where we were in this previous method. So we're going to remember this pointer down here. But for now, we're going to go up and we're going to execute the code that is in this other method called factorial because that's what we were told to do. So what's going to happen is onto our function stack, we're going to push a new method, which is factorial, and it was passed a 4 as an argument. So n comes in as 4 up at the top. And now we are going to execute the statements in here until we are done. At some point, hopefully, we will eventually be done with this method and we're going to come down here and continue on in main. The only thing that's going to be weird here is that somewhere inside of this code, what's actually going to happen is we're going to call ourselves again. All right, so let's see what's happening. So a 4 came in here and n got assigned the number 4. We're going to go through and we're going to do our print statement because that's the first thing that it does. So that's going to print out the number 4 for us. Now we're going to go on to the next statement. Is n equal to 1? Well, no, 4 is not equal to 1, so we're going to skip over this and we're going to go down into the else method. All right, so now the crazy starts. Because we don't know the answer to 4, that's not a predetermined thing, we need to start again and call factorial again, but this time we're going to ask it to calculate 3 instead of 4. And eventually we're going to multiply that by the 4 that we have here. Because again, remember factorial is 4 times the factorial of 3. So in order to calculate that, I got to go figure out this factorial of 3 first, because I don't know what the answer to that is, so therefore I can't return that. So this method, or this line of this method, says result is eventually going to get assigned 4, which we know, times this random thing called factorial of 3. I don't know what the factorial of 3 is. This is a function call, so we are going to go ahead and make a call to the function that happens to be named factorial, which also happens to be the function that we are working on. So in here, we are going to remember that we left off when we were trying to calculate 4 times factorial of 3. But as I say, that means there's a bunch of stuff down here that's eventually going to need to be dealt with. It is not done. This function cannot return until it has calculated this weird 4 times factorial of 3, which means we're going to get a new thing on the stack, which was a call to factorial of 3. In this case, n is equal to 3. And all of what was going on in fact4 is going to sit there and continue to wait until we get our answer back. Cool, so here we are, factorial of 3. So we're going to print n. We get out our little 3, life is good. Is 3 equal to 1? Nope, certainly isn't. So we're going to come down here to this next statement. All right, well this next statement says the result is going to be 3 times the factorial of 2. And I think you can see where we're heading here. So the factorial of 2, we don't know the answer to that. That is a method call, so it's going to cause us to leave all of this work as pending work, and then we're going to continue off and we're going to call the method called factorial, which happens to be us, and we're going to pass it this time 2, because 3 minus 1 is 2. All right, so that starts yet another thing on the stack. Please notice our stack is getting bigger and bigger and bigger here as we go. And we're going to talk about that a little bit more in the end. All right, so we start off this time, n is equal to 2. We print out the 2. There it is in our output. Life is good. Is 2 equal to 1? No, it is not. So we're going to go down, and it now says the result of this is going to be 2 times the factorial of 1. All right, we still have more pending work. That's going to eventually have to be done when we come back. But for now, we're going to go off and call whatever this method is that's called factorial of 1, and that just happens to be ourselves. So another thing gets popped onto the stack. And this time we start off with n is equal to 1. Okay, print out the 1. Life is good up here. And now, good news. Is 1 equal to 1? The answer is yes. We have now terminated. It means that this is not going to ever do the else part where it's going to call factorial again, because we have gotten to a point where the top of the if is actually going to dominate. That's important. If that did not happen, this would go on and on and on forever. So, yay, we actually have an answer, and the answer is 1. So, this method now is done, because once it gets to this curly brace, it knows that it did the if, so it's going to move on to the next statement after the if-else, which there is nothing there. It gets to the end, and all of a sudden, this method has actually returned, and what it returned was the number 1. So that number 1 is going to get fed in to where we just were in the previous method. Remember, in the previous method, it had said the result was going to be 2 times the factorial of 1. And we just didn't know what the factorial of 1 was, so we went off and we called factorial to calculate it. Well, now we know our answer. It was 1, so 1 is going to get filled in down here. Okay, so now we can actually calculate this, because in this call in the stack, where we were was 2 times factorial of 1, which this turned out to be 1. So 2 times 1 is 2, and so when we print out this n, we get the number 2. And now we move on to the next line of code, which is to return a result. And after this is done, we know that this method is going to pop off the stack because it's done, and it's going to return its answer back. So the answer it returned, to be clear, was this 2 times the factorial of 1, which came out to the number 2. So in our stack here, we are going to return 2. That's going to die. And where's that 2 going to get filled in? Well, it's going to get filled into the previous stack, because if you remember, in the previous stack, we had said 3 is equal to the factorial of 2. And the factorial of 2 is now equal to 2, so we now know how to calculate this. 3 times 2 is 6, and so that's going to print out a 6. That is supposed to say 6. I apologize. All right, and now we're going to return that result. That's going to get fed in down here into factorial of 3. All right, and so back down here, we had 4 times the 6 that we just calculated, and that means 24. That's going to return. Oh, this is printing n, it's not printing result. I'm sorry, that's why it's giving us the 1, 2, 3, 4. And so 24 is going to get filled into the bottom one, which was our call in main. And f is now equal to 24. That's where we left off. So it prints out the 24, and main is going to pop off the stack because main is now complete. Okay, so that's how it works when you go through things. There are a number of things to notice. I'm just going to go backwards up to where we originally were when we started pushing things onto the stack. So back in the very beginning of all of this, we asked what is the factorial of 4? And effectively what happened is we went off and we calculated the factorial of 4. In doing so, we couldn't actually get there because it asked us to calculate the factorial of 3. So that caused us to push another thing on the stack, which was the factorial of 3. And since we didn't know how to calculate that until we knew the factorial of 2, that caused us to push the 2 on there. And since we didn't know how to do that until we knew the factorial of 1, that caused us to push the factorial of 1 on the stack. The good news is we do know how to calculate the factorial of 1, so now each of those things gets to come back to the previous call, fill in the information, and actually return what was supposed to be returned from there. And so you can see the collapsing of the stack if I just run through it. In each case, it's filling the number into the previous stack and then coming back down until we get there. So in order to calculate the factorial of 4, we ended up having to make a whole bunch of calls. Very specifically, at the worst case scenario here, we ended up having to do 4 separate calls to methods. The methods that were called each time were called factorial, and it was actually the same block of code that was being called. The same block of code was calling itself, and it had to do it 4 times. If I asked for the factorial of 19 here, it will have to do 19. This stack would grow and grow and grow all the way up until it gets to the factorial of 1, and then once it knows the factorial of 1, it'll start collapsing all the way back down again to give an answer. So I think you can see why this is a very confusing, but also very elegant solution to the problem. Because you're not having to keep track of a bunch of stuff in variables, you're effectively using this stack as a bunch of temporary variables to calculate things. And the actual block of code that you had to write is really, really simple. All you have to do is realize what this pattern is, and then recursion is very, very simple. You simply just call yourself until you get to the right answer. And then the stack pops off, and you get your 24 as you're supposed to, which is 4 times 3, which is 12 times 2, which is 24. That's how you got to 24. All right, so hopefully that makes sense. So what are the common errors that people make with recursion? Well, the first one is to throw your arms up in the air and say, this is all too confusing and I can't possibly do it. You can. It's really not that bad. You will find that it's hard to get your brain around it, but once you come to the answer, you're going to realize that it's a really, really simple answer. And the way to get to that answer is to always just look for what is the base condition, the thing that's actually going to end it, which they probably are going to give you in the definition of the question, and then how do you get closer to that base condition each time. So, the most common mistake is that you forget the base condition. If you do not put that in there, it's going to run and run and run until it actually crashes, which is really no good. So, let's take a look at that over in Replit. Let's torture Replit a little bit. So I'm here in C#, and I'm going to make a new method, which I'm going to call public static factorial. It's going to return an int, I think is what we're doing. Is that what we did in our slides? Let's see here. Yeah, it was an int. All right, int factorial, and I'm going to pass it in n, which is an int. And again, we have our base condition. If n equals 1, then we're going to return 1. Otherwise, we are going to return n times the factorial of n minus 1. All right, and then down here in our bottom main method, we are going to say, well, sure, why not? Say hello world. All right, so we're going to run that, and hopefully we're going to see some cool output. Factorial of 7 is indeed 5040. Let's just do it with the one that we were going to make that into an n, just so that I don't have to keep changing it in 2 places. And I'm going to make that an n, and then I'm just going to define int n equals 7, and that should give me the same answer, 5040. And it doesn't, because I did something stupid. What did I do? I have 2 double quotes. I can apparently have 2 double quotes or no double quotes today. All right, so we should get 5040. The example that we just did was the factorial of 4. And we saw that that was equal to 24, and so this does calculate it correctly. Let me go ahead and set this to 20. You're going to notice that that takes a moment. And you're also going to notice that I overrode the length of an integer. So let me go ahead and change all these to longs, just so that I can actually get back an answer. Okay, so that's a huge number. It actually gets really quick, or gets really big really quickly. How many times did it actually have to get called? So I'm going to just throw in a couple of print statements here just so that we can see what's actually going on. Just trying to print it out so that it looks relatively decent. Yeah, I need to know what n-1 is, don't I? Next round, n-1, and we're going to do next round. All right, so we're going to run that, and I didn't put a semicolon. Okay, so you can see as it was running through here, to calculate the factorial of 20, it got called on 20, and it said, well, that's equal to 20 times the factorial of 19, which 19 is the factorial, 19 times the factorial of 18. 18 is 18 times the factorial of 17. Factorial of 17 is 17 times the factorial of 16, all the way down until you get to factorial of 1. And then you notice it stopped calling itself. And that's because at that point, it actually started to fill the answers in and collapse the stack. And if you count all of these, you'll see that it did it 20 times because it had to actually calculate each one all the way down. All right, so just to show you how bad this can be, I'm going to set it to 100. I'm going to let it to run. And we're going to see what happens. Well, it ran, but I actually got the answer 0. Why? Well, because it probably crashed. I'm going to set it to 1,000. Let's see if we can actually get it to output an error. I think it's being very polite. So what's going on here? Actually, you can see it there in the middle somewhere. There's an error. Well, I don't think it ever prints the error to the screen. It tried to do 1,000 calls, but Replit, very specifically, has a very small amount of memory that it's allowing you to use, and the stack is very limited. So it is possible that with recursion, you can put so much stuff onto the stack, you can actually run the program out of memory. So you're occasionally going to get weirdnesses, especially when calculating very big things. If you run this on your local computer, this code will probably work just fine because your local computer probably has more memory than they give you on Replit. I think this is 512 megs. I might be wrong about that, but I think that's what it limits you to in Replit. And all of these calls are all taking up memory on the stack, especially because I said they're all longs, they're taking up a chunk of memory. So my point here is that as it runs, you can run yourself out of memory because you're making so many separate calls and putting them on the stack. So this is not really a concern on a real machine. It will calculate a correct answer on a real machine, and it will give you the answer back. But it is something to be aware of, that anytime that you're doing something that is recursive, especially if the numbers are going to be huge and you're going to do it recursively for a very large number of times, it is possible that you could run your machine out of memory. So just keep that in mind. All right, so that was one of the common programming errors. You forget to put in the end condition and you will run yourself out of memory. Let's actually do that. So I'm going to change this and I'm going to say n equals 1,000. So I've basically made it so that I'm passing in n of 10, and each time it's going to recurse to another number, which is going to be 1 less than 10, And I'm going to keep going until n equals 1,000, which it's never actually going to get there. So what's going to happen is that's going to run and run and run and run and run until it crashes, which will eventually happen. This is called infinite recursion, because I have never given it a case where it will end. So it's just going to keep going forever and ever and ever, trying to find that n equals 1,000. This is the most common mistake. It can happen in two ways. Originally, this used to say, if n equals 1, return 1. And when you call it again, the other common mistake is that you just send it n instead of sending it n minus 1. This has the exact same problem and is also infinite recursion, because it says, okay, 10 is going to be 10 times the factorial of 9. But then to calculate the factorial of 9, it's just saying 10 is 10 times the factorial of 9. 10 is 10 times the factorial of 9, over and over and over and over again. This is useless. So the most common mistake is that you are not looking for the base condition, or you're not moving towards the base condition. And again, we're in that circumstance right now because I forgot to subtract 1 when I was going in. It won't always be minus 1. It may be the other way around, where you're doing plus 1 and the n condition is at the high end, and you're looking for, when it gets to 10, you know the answer. When you get to 100, it knows the answer. Factorial just happens to be one where you need to go down to get to the answer. Okay? So most common mistake, and the thing you need to watch out for, is that you forgot to check for the base condition, or you forgot to move towards the base condition. In either of those cases, you will make yourself some infinite recursion, which is no good. A stack overflow is what I described just a few moments ago, where you just keep running too much and you eventually run yourself out of space. So let's talk about the efficiency of this. Is recursion more efficient than iteration? Well, no, it's not. Honestly, they can both solve most problems. I would say that the algorithm for recursion is often much more elegant. And what I mean by elegant is that the amount of code that you have to write is much smaller. But it comes at a cost, because it's a little bit harder for people to understand. I will tell you that I have known coders who have just decided they are never going to write recursion because it's confusing. And that's not a good plan. You need to understand how to do it, because it's an important concept, and there are times it is the right way to do it. Especially when you get into data structures, which you're probably going to have to take if you're in the CS program or in a game design or software engineering. In all of those cases, you're going to end up having to take a data structure class, and a lot of work in data structures requires recursion. It's the best way to do it. So calculating things iteratively, which is the other option that's using a loop, versus recursively, you can do it either way, and it'll work both ways. It is important that you understand how to do it both ways, and it's important that you actually can do it both ways. But there isn't a particular advantage. It's actually the case that sometimes it's more work to do it with recursion, as you can see, because you're having to put stuff on the stack. So you just need to look at it and see what makes the most sense for what you're doing. All right, so let's do another example. So in addition to our factorial function here, I'm going to calculate power. All right, so let's talk about power. So this is a calculator, and I'm going to say, I'm going to change it to scientific mode. I don't have a button to change it to scientific mode. All right, we're going to say 4 squared, which is done with 4, that arrow, and this. So 4 squared, and 7 years ago, no, 4 squared is going to be 4 times 4. So when you're doing a power, you're taking the number that is the value, the second value that's passed in, and you're multiplying the first number by itself however many times that second number says. So in this case, 4 squared means I'm multiplying 4 by itself twice because of the 2. If I said 4 cubed, which is 4 to the third power, then that would be 64. It's 4 times 4 times 4. So 4 times 4 is 16, times 4 turns out to be 64. And if I say 4 to the fourth power, then it's 4 times 4 times 4 times 4. 4 times. 4 to the fifth power, 4 times 4 times 4 times 4 times 4. 5 times. All right? So hopefully that's what makes sense as to what power is. So let's calculate power recursively. So I'm going to say public static long, and we're going to call it pow. And we're going to take in two things: our base number, which we'll do as a long, and our power number, which we're going to take in as a long as well. All right, I'm not going to call it base because that has a meaning in C#, so we're going to call it base number. That's why it wasn't highlighting it, and that's a good sign that you have done something bad. When the syntax highlighter is going, what now? So just be careful about using things like that. All right, so what is the base condition here? So how do we know that we are done with calculating a power? Well, 4 squared was the first example. So 4 would have come in as the base number, and squared was the power number. So what do? We multiply the base number by itself power times. All right, so the base condition is if you ask for the power of anything to the first power, it's just itself. And I'm just going to prove that with a calculator real quick. So 7 raised to the first power is simply the number 7. And that's true no matter what I give it as the first digit. So 9 to the first power is just 9, 1,000 to the first power is just 1,000. So anything raised to the first power is just itself because you only multiply it by itself once, it is itself. Sorry, you don't multiply it by itself once. It is just itself. Anything raised to the first power by definition is itself. So let's write that out in code. If power, which was the thing that's coming in here, is equal to 1, then what am I returning? Well, it's itself, which was the base number. And I'm returning that. Okay, so I'm going to go down into my little main here, and I'm going to comment out all of this crazy stuff related to factorial, because that's nothing to do with what we're doing anymore. And so what I'm going to do is I'm going to call power, my new whiz-bang function, and I'm going to pass it in 7 and the first power. And I'm going to get back from that an answer. So I'm going to say x is equal to that, and I'm going to define long x. All right, and it would be helpful if I printed that out just so that we can see. All right, so hopefully that makes sense. So I'm calling power, passing in a 1 as the power. And the specific number I'm passing in is 7, so I should simply get 7. Not all code paths return a value. That is very fair because I have written a method. I've declared that method is going to return a long, and then it has detected that if I'm in this path, I return a value, but if I'm not in that path, I don't. So I'm just going to say return 0, which is nonsense, but just so that it doesn't have a compile error for now. All right, so cool. So I have built my base condition, and I've tested that the base condition works. If you pass it any number to the power of 1, it will return the original number. Very exciting code. But if I needed to do something more than that, then let's talk about how I would calculate the next step up, which is 2. How do I do 2? Well, assuming that I didn't return in that first one, we're going to do our else condition. So what I actually need to return here is the base number times the power of power minus, I'm sorry, the pow is the name of my function, power minus 1. All right, now how did I calculate that? So I'm trying to figure out what some number, which we'll assume is the number 5. So I'm going to call it with 5. So base number is going to be 5, and I want to be able to calculate 5 to the second power. So I'm going to get a 5 in here, and I'm going to get a 2 in my power number. That's not going to equal 1, so we're going to come in here. And how do we calculate it? Well, we know that 5 to the second power can also be expressed as 5 times 4. Yeah, that needs to be a comma. I just realized that. All right. Yeah, doesn't need to be a comma. It does need to be a star. The comma needs to be in here. I need to pass two parameters into power. Sorry, confusing myself over here. The base number needs to go back in because I have defined this method as having two arguments. So it's very important that I pass it two arguments when I make a call to it. The first argument is going to be the same, which is the base number. The second argument is going to be power minus 1. All right, so is this correct? This is going to be 5 times the power of 5 raised to the first power, which is going to be 5 times 5, which is going to be 25. That looks quite reasonable to me. All right, let's try it for the third power. So we're going to pretend like this is 5 to the 3. Before I do that, let's run it with 5 to the 2. I should get back 25. And I need to put in a semicolon. Okay, and I did. Let's add in a print statement here just so we can see what's happening. All right. So we're going to see that it's only going to have to make that call once, 5 and 2. And up here, I'm going to add in a console write line. I made that as complex as I possibly could have, and as a result, I forgot the semicolon. Okay, so you can see that it eventually got to a call where it was asked to return the power of 5 and 1, and it knows how to do that. All right, so let's try this with a 3. Does this work correctly with a 3? So we should see two calls. It's going to go up and it's going to say power of 5, 3. All right. So the base number is 5, the power is 3. Is the power equal to 1? No, it's not. So it says I'm going to call it with 5, which is my base number, and power of 2, which gets us one step closer. All right, so that says calculate 5 times the power of 5 to the 1 less than that, which is going to be 2. And then you see you have another call, and so on and so on. Eventually, you get to the point where you're called with power of 1, which that case was 5 to the 1. We know at that point it returns the base number, which is 5. So that gets filled back in to this block down here, and you end up with 5 times 5. Or in the case of the next call, it's 5 times 25, which gives you 125. So hopefully this makes sense. This code is also in here, but it's written ever so slightly differently because they use different variable names. That's the code in C#. That's the code in Java. They are the same. There really is no difference in this case. There's no syntactical difference when you're doing recursion. In both cases, you're simply calling a method. It doesn't matter that the method happens to be recursive. So hopefully that makes sense for this. So to review, in order to make a recursive call, you're going to call yourself. If you're going to call yourself, you better be getting closer to your base condition. And somewhere in your code, you actually have to tell it what to do when you reach that base condition. If those two things are true, then you're going to get your answer back correctly. If those things are not true, you will have infinite recursion. So hopefully that makes sense to you guys. I would strongly encourage you, before you go to bed or whatever it is that you're doing tonight after watching this video, that you attempt to write the same power function that I just did by yourself. Without looking at the code from this video, open up a replit in your language, whether it's C# or whether it's Java, or open up your IDE, IntelliJ or Visual Studio, and attempt to rewrite what I just did with power. And if that makes sense to you, then maybe try to rewrite it again with Fibonacci, which I think is a number that you guys are familiar with, where it's 1 Fibonacci of 1 or 2 is equal to 1. The Fibonacci of everything else is the sum of the previous two numbers. So that's another good example for writing something with recursion. Again, the only way this is going to make sense to you is if you write examples. So I'd strongly encourage you guys to do that. This has been the lecture on recursion.